is my good friend Chen. And as you can see, we have decided to take a little break from the usual deep learning applications. No diagnosing disease or driving cars today. Instead, we are ventured into something much more crucial to our daily lives. Mastering the game of 2048. Yeah, you heard me right. We are teaching AI how to beat one of your favorite procrastination tools. Our project, Swipe Right to the Glory, isn't just about getting one single tile to 2048. It's about pushing the boundaries of a strategic decision making on the randomness of the tile spawns and handling the stress of a fully occupied board without flipping the table. We employ some pretty slick techniques like behavioral cloning, adversarial inverse reinforcement learning, and our star plane, the generative adversarial imitation learning, which is GAIL for short. Why GAIL? Because it learns from the expert swipes without needing to peek at the underlying reward function, which is great because who really knows what rewards await at the swipe of the tile? And what did our AI learn? A lot about patience, strategy, and maybe a little bit about like extensional strat as it faced the endless combinations of the tiles. Think about the policy model as the brain of our AI. So it's built on a simple intuition. We need a feature extractor, which is the ResNet here, a memory unit, for example, LSTM, and the decision-making unit. So here we use the transformer. This formed the core of our policy model. Around this core, we also added the embedders, output format units, and the head of for the complete setup. Intuition is a great start, but it's rarely enough. To test our model capabilities, we designed a straightforward behavior cloning test. Here, the model learns from the expert data, 50,000 games with over 60 million steps. Sounds impressive, huh? But it's far less than 1/10 billionth percent of total stair space. If this model cannot nail a basic task like that, there's just like no way it's gonna success with harder RL tasks. So initially, our model only hit like 50% accuracy after 100 ECOPS, so not really ideal.
So we went back to the drawing board and improved. There are two key milestones here. The first one is we realized that we don't really need a memory unit. The game essentially depends on the current state to determine the decisions or actions. So we removed the RNN block by another transformer block, which greatly improved the accuracy for the behavior cloning task by around 20%. So we reached around 73% accuracy there. And the second milestone is that we realized flattening the 2D features too early will cause us to lose the key vertical features. So we switched the ResNet with 2D convolution layers and added positional encoding after the ResNet and before the transformer. And by that, the final version mastered 6 million step tests in just 10 epochs with a 98% accuracy. And now we're going to talk about the model training flow. Like we use a very standard GAIL training flow with some minor tweaks in each step. So the first tweak we have is in the data collection phase, where we collect the agent data. We find that the agent tend to start on some full board state and gonna exhaust the replay buffer. So we make an early stop mechanism to prevent the agent to stuck in the same state for like 2,000 steps. So if we observe that the agent stay in the same state for around 20 steps, it will restart. And the second trick we have is in the data sampling for the expert during the discriminator training process. We don't want the discriminator to find a shortcut by just looking at, well, the higher tail is the expert, while the lower tail is our agent. So we try to cut the expert trajectory by a point that is not clearly better than our agent. And lastly, in the policy training process, we add a little adjustment on the reward function here. Is to penalize the agent for staying in the same state for too long. Like it's just to compensate the early stop mechanism, like preventing the agent from exploring the game.
So in conclusion, while our AI wasn't busy watching YouTube, it was actually learning how to make smarter moves. Sometimes even outperforming one of our best players here. So who knew that neurons can actually crave the sweet of victory that the 2048 tiles, just as much as we do. So next time when you are approximating with the game of 2048, just remember somewhere an AI is probably outswiping you, learning the best moves you've never thought of. But don't worry, we're not training it to do homework yet. So thank you, and let's just keep swiping right in the game of AI, and maybe in the game of our lives too. Thank you. Questions?
Questions?
Good storytelling. So I see that you try with Gale, etc. Have you
Yeah.
played on like harder games like 4060, 96?
Try to play until that.
Play on the harder version of this game. The best score is double. It's 4096.
Like
So the bridge will be bigger, etc. Like testing generalizability.
you mean like say if it can reach beyond the 2048?
Yes, because you have reached like 99 or 100.
That's on the behavior cloning task.
Oh, there you go.
Yeah, to just simply test the capacity of the model.
Yeah.
Well, our model is not that good. Like the
No,
best
it's
score
not.
is Intel 512.
But the point is that they could beat the random policy, which means that the model is getting trained. So yeah.
Yeah, I feel like if we like more computing like
Sure, definitely,
capabilities,
yes.
definitely it's gonna be there. It's just like we just don't have that resource, right?
So if you would have shown any other figure close to that one, then I wouldn't have voted this. It couldn't be the case, like
Yeah.
the processing units that you have. One question, how the environment, you got it like already implemented, right?
Yes.
So where did you have it? Like it was already available in Gym or?
No, we implement everything ourselves.
So the
for the environment, you implemented this from way around, right?
Yeah.
Oh, okay.
So the data we collected from the internet, but we basically like starting everything like all the layers or the models that you're seeing like from very scratch. Because we didn't like find any like resources, and then we feel like it would be like more practical for us to like implement from like zero.
Okay. And what do you have? How did you have, or how did you get access to this expert data?
It's
So-
by looking at
Yeah, there's a website like just giving us like a sample data, like giving us like expert like moves, like what kind of moves they're having and what kind of scores along the way. So we were originally like using that to train this data to train this model actually.
So there's an expert policy off the shelf.
Yes. It is a model-based policy. It's not a zero.
Oh, yeah, what is the architecture of your generator and discriminator? Maybe you said it, I didn't.
The final one is for the generator is start with the ResNet with 2D convolution
This
layers,
one, yes.
and then followed by two positional encoding block, and then flatten it with 2 transformer block,
Okay.
and then add Fn as the output format unit, and follow with 2 linear heads.
And the discriminator?
The discriminator is rather simple. It's just a bunch of convolution layer to handle the spatial information, and 1 linear layer for the action, and combine them together to use Fn for the final result.
So are you using ResNet as a C because we can actually embed the grids with vectors in
We already embedded it by embedder, and because we majorly want ResNet to extract the row and column features, because like the measure of like combining tiles is, let's look at the adjacent one.
what?
Like you need to look at like which tiles are adjacent to each other to combine them.
Then I mean we can just fit the 4x4 grids or flatten to 16-dimensional vectors is enough to represent the grid itself.
Yes, that's what we did in the beginning. So we flattened it at the very beginning, and we realized that it lost all the column features. because like the version 2 and version 3 of our model, the key difference is where we flatten this feature. Is they all have a ResNet and they all have 2 transformer blocks. But version 2 is flattened at the very beginning and it's only have like 73% accuracy on the Pentatonic task. But after we move the flatten to the middle, it's much better. Like we get 98% accuracy in 10 epochs against like 73 in 100 epochs.
Gotcha.
Good, thanks.